Aloha, this is RBrewer with the Hawaii Department of Health. This is a recording of a presentation I originally gave to the San Francisco Bay Area Regional Water Quality Control Board as a part of California EPA on August 23, 2016. It's entitled Why Discrete Soil Vapor Samples Lie and Why Sampling Theory is Important. This is actually an extension of some work our office has been doing with a number of other people for the past 10 years, looking at the implications of random small-scale variability on the use of traditional discrete sample data in environmental investigations. And by discrete data, we're referring to samples collected from a single point and of a very small mass and a very small volume. So let's take a step back for a minute before we look at soil vapor and look at some of our soil data results. This is the title of a presentation I gave at the Patel Conference in Palm Springs, California, in May 2016. Similar title, Why Discrete Soil Samples Lie and Why Multi-Increment Sampling is Important, a field study of heterogeneity. So what we're undertaking right now is a field study of heterogeneity with respect to soil vapor. Let's look at the results of this study. First, what are the origins of discrete sampling methods to begin with? If you look back at some of the early environmental guidance written in the 1980s when the RCRA and other important federal environmental regulations were being passed in the U.S., most of the discrete sampling methods were based on experience at that time with testing industrial chemicals and waste. So here's some quotes from some key guidance documents written during that period. So from the USEPA's 1985 verification of PCB spill cleanup guidance, it's the basis of TSCA regulations and a lot of other guidance on collecting soil samples. So the implicit assumption that contamination is likely to be uniformly present anywhere within the sampling area is reasonable. So they're saying within a given spill area, you should get the same concentration from one point to another without much variability. And in line with this, the PC level is assumed to be uniform within a contaminated zone spill area and zero outside of it. So very sharp boundaries, very uniform within spill areas. Another quote from another important EPA document written at the time, Methods for Evaluating the Attainment of Cleanup Standards. When there is little distance between points, it is expected that there will be little variability between points. This all comes in the idea of co-located samples. If you collect one sample just a foot or so away from another, you should get roughly the same answer. So this has very important implications. If these assumptions are true, as they are probably for a lot of, say, wastewater sampling from industrial plants, unless the process changes, then with respect to soil sampling, the location of the sample within the targeted area and the mass and volume of the sample collected are not important. This greatly simplified environmental investigations, and in the end, environmental laboratories are essentially in charge of telling consultants how to collect samples in the field. They tell you how much soil to collect, say 4 ounces, just based on what they need in the laboratory. And in reality, they also told you how many samples to collect. So there was a limited resources available for collecting samples. So you took the money available for analyzing samples, divided that by the cost per sample, and that was how many samples you could collect in the field. So it really simplified things, and it put the laboratories in charge of field work to a large degree. Well, here's the reality. This is from our field study we carried out in Hawaii a few years ago. It's published last year in 2015. So contaminant concentrations in reality are highly variable and random at the scale of a small volume discrete sample. So the examples shown in these photos here were from a PCB site, and the first photo on the left, it's a sample that we split into 10 subsamples and had tested independently. So you can see the range of concentrations within the sample. PCBs 810 ppm all the way up to 5,700 ppm within a single jar of soil. Again, we split this into 10 separate jars, had the lab test each jar with an average of 2,400 milligrams per kilogram. So almost an order of magnitude variability within a single sample. We saw a lot higher variability in this on average in our study at the PCB site for individual grid points. How about we refer to this as intra-sample variability. So look at inter-sample variability from our field study for soil. These are for variability between what you refer to as co-located samples. This is the same grid point. You see the individual grid points around individual samples around this grid point range from 4.9 ppm PCBs to just a foot away 91 ppm PCBs. And there you can see circled in red, that's the sample that we had split up into 10 individual jars and tested independently. It came out 2400 ppm. So there's a huge amount of variability within a very small area around a grid point. One thing to point out is this variability is totally random. PCB concentrations weren't increasing necessarily in the direction of the 91 ppm sample or decreasing in other areas. It was completely random. These are published results of this study published in a report, Small Scale Variability Discrete Soil Sample Data. It's available on our web page. Also, we have a paper in press, a critical review of discrete soil sampling methods. Hopefully it'll be published sometime this fall. So as Dr. Phil might say, how's that working for you? These are very common soil investigation problems that we've all dealt with for the last 10, 20, 30 years. Very common a need for multiple remobilizations and step-out investigations as you find some contamination with individual discrete samples but are uncertain of the extent. And there's really no clear endpoint to these investigations. It creates a lot of brownfields in many cases. Also, failed confirmation samples. You've taken individual discrete samples around what you think is a contaminated area. They come up clean, you excavate that area, you go back and collect more confirmation samples, and some of them fail. Again, very common to see. And also accidental import or export of contaminated soil. We've seen a big problem with that in Hawaii with soil that was tested using individual discrete samples. And it's just very easy to miss contamination when you're only testing a spoonful of dirt at a time with a small number of samples. This is what random small-scale variability looks like in the field. And this is PCB data for, I think it's a 9-acre site. Several hundred individual discrete soil samples were tested for PCBs. So one thing to note here, and you'll see this in a lot of other types of data, is these seemingly isolated hot spots and cold spots within the area. And once you start seeing these types of spots, it's a big red flag that you may be dealing with random small-scale variability or heterogeneity. Large-scale patterns in this data set are probably real, and the consultants who did this knew the problems with heterogeneity. They were just looking for large-scale patterns. So there probably are more PCBs on the left-hand side of this site, or higher concentration of contamination. The smaller scale patterns within here are probably artificial though, and probably wouldn't be reproducible. So if you went back and resampled this site, shifted the grid over a few feet in any direction, you'd probably see a very similar pattern, but all these seemingly isolated hot spots and cold spots would have shifted to new positions. That's how you identify random small-scale variability. Here's a more realistic interpretation of the data, more realistic resolution. And again, this is what the consultants wanted to use it for. It's just to identify very large-scale patterns of contamination at a site, and then you can go in to these areas, or the whole area in general, and designate decision units for more detailed and more rigorous multi-increment sampling. You could use the discrete sample data for initial removal actions, or maybe initial actions at a site, but you always want to collect MIS data for confirmation. So that's how sampling theory has been incorporated now into soil sample collection. So that the first point is you designate a decision unit or an area of soil where you want to make a decision on, and then you collect a large mass or large volume sample within that area, a single sample, have it analyzed and properly processed at the laboratory. So then the resulting data that you get are going to be representative of the sample you sent to the laboratory, and they're representative of the area where you collected the sample in the field. So this concept of decision units is real critical to sampling theory and to data reliability. And we have just updated our guidance on DU-MIS site investigations. It's posted in August 2016. We have other recorded presentations on this topic. So that's heterogeneity in soil. With the indoor air, people are way ahead of us when it comes to environmental investigations. They've been looking at indoor air, heterogeneity in indoor air for many years, and especially getting much more detailed data recently by the use of a continuous indoor air monitoring, continuous sampling. Here's an example from Blaine Hartman and Mark Cram presentation they gave at the same Patel conference in 2016. Continuous monitoring over several days within some type of former industrial building. You can see the peaks. They're looking at PCE. See the peaks of concentration of PCE in indoor air during the nighttime, and then it drops back off during the daytime, goes back up at nighttime. So this is actually happening when the HVAC system is cut off at night or cut way down. So these peaks could be due to indoor air sources. You get an increase in PCE concentrations in indoor air when the HVAC system is running less or actually turned off. It drops back down during the working hours during the daytime when the HVAC system is turned on. This could also be due to vapor intrusion, which is what they actually suspect. In this case, if the building was air conditioning during working hours, this would create a higher pressure inside than outside, and it would keep vapors from intruding into the building. So the indoor air folks have been, I'd say indirectly, maybe unknowingly, incorporating sampling theory in indoor air studies for a number of years. So they've gotten much better understanding of small-scale variability of VOC concentrations in indoor air, and then they're getting much better at specifying a specific exposure period, or what we call in sampling theory decision unit, for sample collection. Now, depending on the objectives of your study, this could your DU, decision unit exposure period, could be hours, it could be days, more likely it's weeks, or if you're looking at chronic exposure, it could be years. So the sample collection method is designed then to capture or exclude, if you're not looking, say, at nighttime concentrations, small-scale variability of VOCs in indoor air. And what you want to do is obtain a representative sample, representative data for the designated exposure period decision unit, volume of air. Decision units are always of volume. They're based perhaps on a time period, but really what you're trying to do is collect a sample from a specified volume of air flowing through a building or home during a specific time period. So for example, if you look at EPA's vapor intrusion guidance, the default indoor air exchange rate, let's say of half a time per hour, or DTSC in California EPA the same way, in a 244 cubic meter building, this results in a daily volume of air flowing through the building of around 3 million liters of air. So your task might be to collect a representative sample of that 3 million liters of air flowing through a building in a single day. So these are all great. The representative sample you collect, the resulting sample you collect, is intended to represent very large volumes of air, millions of liters in general. The same thing we're trying to do with soil samples. Collect a relatively small soil sample that represents a very large mass and a very large volume of soil. So these are very good, and I'd say rare in the environmental industry, examples of incorporating sampling theory in an environmental investigation. So that was soil and indoor air, looking at heterogeneity. Let's look at heterogeneity in subslab vapor plumes now, more the topic of this presentation. So this is a map you see on the left from Mort Smit, who's one of the co-authors on our vapor intrusion paper we published last year, or 2 years ago now. So Mort has a lot of experience in collecting subslab vapor samples. In this particular building, this is a 25-foot grid spacing. It collected 86 samples. The floor area of the building was about 45,000 square feet, say 4,200 square meters. But here you see something very similar to what we see in soil data. If you plotted up indoor air data, looking just at temporal changes, you see very similar things. The large-scale patterns are likely accurate. There probably are higher concentrations of, I think this is PCE vapors in the right-hand side of this building compared to the left-hand side of the building. But you really have to start be worrying of these artificial hot spots and cold spots. If you look more closely here, the hot spots based on a single sample, so that throws up a quick red flag. The same thing for these white and gray areas you see in the map, or cold spots. Most of those are based on just 1 or 2 samples. So think about this in more detail. The subslab vapor volume under here, if you assume a depth of 30 centimeters, about 1 foot, 30% porosity, it's about 400,000 liters under this 4,000 square meter building. They collected 86 subslab vapor samples. Each individual sample was about 1 liter. So each of the grid cells represents an area 25 feet by 25 feet. So translate this into volume for a depth of 1 foot and convert that to metric. It's about 5,000 liters. So each one of these sample points is intended to represent about 5,000 liters of soil vapor. So what's the chance that grabbing one random 1 liter sample within those 5,000 liters is representative of the immediate area surrounding it? You'd really have to assume a lot of uniformity at a very small scale for this to be true. More than likely, these single sample hot spots and cold spots are just artificial, and they're just reflecting small scale variability within larger scale patterns. So if you're going to make decisions based on single samples, you really have to look at other potential lines of evidence, looking at where you suspect potential releases could have occurred, drains and cracks, historic releases and such. So again, similar to soil, similar to indoor air, large-scale patterns and trends are probably accurate. Smaller scale patterns within these large-scale trends very well could be artificial, just artifacts of heterogeneity. So let's look at the implications for vapor intrusion investigations, and especially the development of subslab attenuation factors. So subslab vapor data are very important to establish the link between potential recognized indoor air impacts and subsurface contamination, especially if you happen to own that building or be responsible for contamination in the area. So as part of this, it's the estimation of a subslab vapor attenuation factors. It's a very critical parameter for vapor intrusion screening. So I want to look at this in a little more detail, and we'll look at the influence or implications of small-scale variability on how these subslab attenuation factors might be calculated or estimated. So we'll start backwards. First we're going to look at method 1 and method 2. There were two different methods developed by EPA or published in EPA guidance over the last 10 years or so. Method 2 is published in their 2012 document on their empirical database. So in this case, the subslab attenuation factor is calculated very simply. You collect one sample of indoor air and you collect a sample of the vapors under a slab, and that ratio is assumed to represent the subslab attenuation factor, or the attenuation of vapors as they intrude into a building. So this has a lot of interest. It's intuitively more direct and accurate, and USEPA has a database for hundreds of homes and buildings with this type of data in it. And then you have lots of numbers. You can calculate generic attenuation factors based on a statistical evaluation of the database. It's very tempting to use this type of approach. And that's what they did, and this is from their 2012 guidance to some of their subslab data. In this case, looking at the purple line, they estimated a median subslab attenuation factor of 0.003, or about 300-fold attenuation of vapors as they intrude into indoor air. They estimated a 95th percentile attenuation factor based on one subset of that data of 0.03, or only about a 30-fold attenuation of vapors as they intrude into indoor air. The assumption was that this 0.03 attenuation factor could be assumed to be relatively or reasonably conservative for use in screening levels. DTSC, the Department of Toxic Substances Control, California EPA, used a default subslab attenuation factor 0.05, or about 20-fold attenuation, based on their reviews of this database. A lot of us were looking at this database. I spent several years playing with it and looking at it before I realized something might be not quite right. So here's the first problem. Again, I live in Hawaii. I've lived all over the U.S. and a lot of places in the world. One thing that's very clear up front is one size doesn't fit all for attenuation of vapors as they intrude into a building. First problem that comes up is USEPA's database the data are mostly from very cold areas of the U.S., the Northeast and the North Central states. Also, a majority of indoor air samples were collected from, or more than likely were poorly ventilated basements. So they're probably not representative of normally occupied areas. It could be excessively conservative. And there's a temptation to use the 95th percentile subslab attenuation factor, but this assumes that a building essentially heated year-round and with a very high vapor flux, and that definitely wouldn't apply to places like Hawaii or even the central coast of California and other areas. So the first problem was that applying a single number to the entire U.S. was just excessively conservative, and we could do much better than this. A much bigger problem that we're starting to recognize now, and getting back to heterogeneity, is reliance on a single subslab vapor sample to calculate an attenuation factor. They did this for 85% of the individual homes and buildings in the database. At most, they looked at 3 samples, really, for just a few of the hundreds of buildings that they looked at. So think about this: when there's tens of thousands of potential 1-liter vapor samples under a single slab, and you randomly pick one of them, what's the chance that that's representative of the intruding vapors? Again, going back to the 1980s era guidance, you'd have to assume a significant degree of uniformity of vapors and VOC concentrations in vapors under a slab for this to be true. And we've already seen in the earlier slide that this very likely isn't true in all cases. So increasing number of samples typically reveals an increasing small-scale spatial heterogeneity. The more you look under a slab, especially when you're looking at a resolution of only 1 liter, the more heterogeneity you see. And you'd expect that based on soil type, moisture, preferential pathways, air movement around the edges of the slab or under the slab. So this has a lot of implications for the EPA's empirical database and the use of it to estimate subslab attenuation factors. This is another figure of a subslab vapor plume. In this case it was TPH under I believe this is under a home, much smaller area. But again, if you look at this, the VOC concentrations under slabs can vary by orders of magnitude. And the calculated subslab attenuation factor depends on where that one sample was collected. So if you look at this figure, the X's are example points of where a subslab vapor sample might be collected. That's going to you're going to take the indoor air concentration and divide it by one of these X's to get an attenuation factor. And it's real clear up front that your attenuation factor could vary again by orders of magnitude. So the representativeness of a single small volume sample for intruding vapors is unknown due to both heterogeneity, and also you have no idea in most cases where the vapors are intruding. So the potential error in estimated subslab attenuation factor for a single building isn't quantifiable. You have no idea how far off that number is. This has a lot of implications for the empirical database, and we've talked about this before. We discussed it in the paper we published in 2014. So the accuracy of individual subslab attenuation factors is unknown. Again, the error in the extrapolated generic attenuation factors for any given data point isn't quantifiable. And you can't, it's a common problem, and I've had this in the past, I'll be the first to admit, you can't fix problems like this by statistical analysis. A statistical test only evaluates the precision of that test to estimate a mean for that specific set of samples that you run through the test. It doesn't tell you anything about the potential error in the field. That has to be looked at separately. So the empirical database EPA put together, while highly worthwhile at the time, it's not scientifically supportable for estimation of attenuation factors. Now, one very interesting thing with this is the median value actually matches up very well with our estimates in the paper we published for cold areas of the U.S. using the original US EPA method. So it actually might be useful. It appears to be useful. But the 95th percentile and other values away from that just represent noise in the data, and you have no idea what the error is in these numbers. A great book to read if you haven't read it before is it's called The Signal and the Noise: Why So Many Predictions Fail But Some Don't, by Nate Silver. He talks about sports and investment a lot, but the ideas he has apply definitely to environmental data. So this isn't a new thing. Here's a quote from a 2005 EPA guidance. Actually similar quotes in several other guidances written by US EPA in the early 90s. Geostatistical techniques are not a substitute for proper sample collection. So again, it gets back to the same point that the sample representativeness is important. If your samples aren't representative of what the area where you collected them, then that's going to introduce a lot of error into the database and error into any conclusions you make or statistical analysis of the database. Now, California EPA, when they published their vapor intrusion guidance in 2011, were well aware of this. Is a quote from that guidance: "The default attenuation factors assume that the subsurface is reasonably homogeneous or reasonably uniform." And now we know over the past 10 years, especially the last 5 years, that this just isn't true. So why do we keep clinging on to this, and why myself, I looked at the database for years before I finally started realizing what was going on, accepted what was going on. This is kind of interesting to step into psychology. It's an effect called the endowment effect, assignment of more value of something because you happen to own it. So let's assume in this example here a consultant submits PCB data for 30 discrete soil samples collected within a residential yard exposure area, and the goal is to calculate an arithmetic mean and then a 95th% UCL, and use this to quantify excess cancer risk. So you've done that, submitted it to the regulators, but lo and behold, the laboratory discovers that the equipment was malfunctioning on the day of sample analysis. So the reliability of any single data point is uncertain, and the range of potential error within any data point in your calculations in general is unknown. So think about this: does the consultant still think that risk conclusions are valid? that they submitted in their initial report? Well, possibly they could. But would a regulator accept the 95th percent UCL and the estimated risk based on this data, knowing that the lab is uncertain of any given data point with the accuracy of them? Well, there's no way a regulator would accept it. They would say start over. But again, that's the problem we have with the database, EPA's database, is that it was our database. That's why we've clung to it so long. It's because it was ours. I think we just didn't want to accept the reality that it's not reliable. This has a lot of implications for vapor intrusion investigations. Again, the use of excessively high subslab attenuation factors, we're assuming minimal attenuation of vapors intruding into a building. It causes a large number of low-risk sites to be unnecessarily flagged for potential vapor intrusion risk. And we discussed this during the presentation I gave at the Regional Water Board in Oakland back in August. And the larger regulatory agencies like USEPA and DTSC, they tend to focus on a very small number of high-risk sites. So they don't really see the implications of this, or the effects that using excessively low attenuation factors and then in turn excessively low screening levels have on property owners and businesses. But they really can impose a significant and unnecessary legal and financial burden on affected parties. I talked to a lot of small business people who are about to lose their businesses or lose their loans to expand their businesses because they had been flagged for potential vapor intrusion risk with very minimal concentrations, say, of PCB in groundwater because of these excessively high vapor attenuation factors that were used to develop some screening levels through EPA and other agencies. This has very adverse effects on business and property owners, again, not seen by most regulators. Around 75% of site investigations never go through a regulator. They're done for private property transactions. And the problems you see, just unless you happen to be talking to these people, like I spend a lot of time in my job doing, you would never know what's happening. So the continued use of this database also really conflicts with the US EPA scientific integrity policy. And to quote it below, science is the backbone of EPA's decision making. The environmental policies, decisions, guidance, and regulations that impact the lives of all Americans every day must be grounded at a most fundamental level in sound, high-quality science. So that's something we need to keep in mind when we're looking at past policies that we come up with, even current policies. How sound is our science? And just be aware of the impacts it has on the regulated public. So really, that was method 2, the vapor intrusion database. It's a great idea, very worthwhile doing. The median might be correct. That tells us a lot about vapor plume heterogeneity. Maybe it's not as high, definitely not as high as we see in soil. But again, the reliability of the attenuation factors gets to be very questionable, especially when you start to move away from that any central tendency, like just a simple median. So let's go back to method 1. This is the original US EPA method in their 2002-2004 vapor intrusion guidance. It's used in a lot of other scenarios also. In this case, the subslab attenuation factor is based on the estimated vapor entry rate, say in liters per minute, divided by the indoor air exchange rate inside a building in liters per minute. So this is a very well studied and field tested by building design engineers, radon experts, and other people. It's not just a theory. There's a lot of data behind it. So it's another database approach that's been developed into a model. Again, it was the original model in US EPA's vapor intrusion guidance. It's also discussed in California DTSC's vapor intrusion guidance, at least the 2005 edition. So this is very common. This was a red flag for some of the vapor intrusion guidance that I think I helped prepare in the early 2000s in EPA's guidance and other agencies' guidance now. Is this concept of vapor leakage. It goes all the way back to the 1940s. It's when people started air conditioning and heating their homes, there were concerns about vapors or about cold air coming up through the floor or losing air conditioning out through gaps in the walls and such. So these building leakage models, they're quantitative, but they've also been field tested for decades. And a lot of times they're required under building permits to follow these models in your building design. And then post-construction leakage tests are often required by the permitting agency just to demonstrate that the building is both tight enough to meet energy usage concerns and also leaky enough to meet indoor air quality concerns. So and again, leakage tests also like this are often used in indoor air studies. They've been around a long time. So there's a big red flag that goes up in vapor intrusion guidance, some that I wrote, although we changed our guidance now. But say in EPA's more recent vapor intrusion guidance to other agencies, there's no reference to building leakage studies done by HVAC building engineers. Here's just a few of the classic references, and these are updates by ASHRAE of field method to determine air exchange rates in detached dwellings. These all talk about building leakage, including leakage through the floor. And then the International Code Council, International Energy Conservation Code and commentary, they go into a lot of detail on building leakage models and building design and such. So there's an idea that these method 1, some people are calling it the vapor flux method, is just pure theory and just based on a model. That's not the case at all. It's actually well founded in field studies and databases that go well beyond anything we've done for vapor intrusion databases in the past 10 years. So here's some example of default subslab attenuation factors using this method 1. First, California DTSC in their 2011 guidance, they have default model factors that you can use to calculate what there's site-specific attenuation factors or site-specific screening levels. In this case, they're assuming a vapor entry rate of 5 liters per minute. That's very well grounded in building leakage studies. And indoor air exchange rate, they assume of half a time per hour. So if you look at that based on a 244 cubic meter home, their default comes out about 2,000 liters per minute indoor air exchange rate. So 5 divided by 12, their vapor intrusion default subslab attenuation factor is 1/400, about 0.0025. So there's that number again, 0.003, just like we saw in EPA's empirical database. That appears to be a good number. In Hawaii, we don't heat our homes, so we have a much lower vapor entry rate because we don't have that high of a pressure differential to drive vapor flux. Also, we leave our windows open much more of the year, in my case every day of the year. So even a conservative estimate in Hawaii, a vapor flux rate or vapor entry rate through the floor of building due more to wind effects here, about 2 liters per minute. Indoor air exchange rate higher than you'd see in colder parts of the country. Here we're assuming 4,000 liters per minute. So this leads to a default subslab attenuation factor of 1/2000, so 5 times less conservative than California's, 0.0005. And that was just published in our updates to our environmental action levels. So that's a key point, and I don't think very controversial, that vapor intrusion risk is going to vary in different parts of the country and based largely on differences in indoor air exchange rates and vapor entry rates that are to a large degree based on climate differences. So in a very important paper published in 2014, Sungadal came up with a method to estimate subslab attenuation factors on a very climate-specific basis. And all they did was take the building leakage models that are been used for decades again in building design, and then couple that to the vapor intrusion models. These building leakage models, one of their key uses is to estimate differences in building pressure differential, the delta P in the vapor intrusion models. All this is the difference in indoor air pressure versus outdoor air pressure. And this is really what drives vapor entry into a building. So if you know the delta P, or the pressure differential inside of a building, and you can estimate the average area of cracks in the floor of a building, then you can estimate fairly accurately the vapor entry rate into that building. So that's all they did. They took the building leakage model and coupled it with the US EPA's vapor intrusion model, and they used this to generate a daily vapor entry rate by also incorporating region-specific climate database. So here's the result of this. They ran this in a similar area that US EPA used for their database. They were collecting their samples. So in this case, and not surprisingly, you see in the graph here on the bottom, on the y-axis on the left is the modeled vapor flux rate on a day-to-day basis, and then days of the year on the bottom. So this is based on, for this particular year's data, the wind factors like temperature, wind speed, and other issues that would help drive indoor exchange rates, or in this case especially vapor entry rates. So during the winter time, this is starting in January, you'd see a higher vapor flux rate into a building when it's being heated. Then in the summertime, in the middle of the graph, you see a lower vapor entry rate or vapor flux rate into the home when it's being cooled, and near zero when the windows are open. and if there's no wind blowing, and then it starts to increase again in the fall. So what's key about this is you see differences in vapor entry rates or vapor flux rates based on the climate of the day. So what you can do is take this exact same approach and apply it on a larger scale basis to look at regional climates instead of daily variability within a single climate zone. So that's essentially what we did. Here's an example climate-based vapor flux rates or vapor entry rates. Flux just means it's the vapor entry rate per area. So on heating days, when homes are being heated using their models, again just standard building leakage models, we can assume a vapor entry rate through the floor of a home of 4 liters per minute. Again, this is for a 100 square meter, 1,000 square foot home. On cooling days, when the temperature is greater than 65 degrees, we can assume a lower vapor entry rate. Just less, that pressure differential is going to be less of 2 liters per minute. And we can use this to develop region-specific annual average vapor flux rates based on the number of days below and above a mean temperature of 65 degrees Fahrenheit, or if you live in Mediterranean climate, the central coast of California, 55 degrees, because in that part of California, if you've ever been to San Francisco, people don't start heating their homes in general until the temperature drops below 55 degrees. So that's what we did in our 2014 paper. Is first we look at large-scale climate zones used by the building design folks, and split the U.S. up into 4 different climate regions. And region A was cold, region B warm, region C more Mediterranean climate, again in coastal California, region D is tropical. And associated with each one of these, based on climate databases, again used by the building engineers, we can specify a number of days when the temperature is going to be above and below 65 degrees Fahrenheit, or 55 degrees for Mediterranean areas. So for example, in the region A, in the cold area, the average of 303 days where the temperature is less than 65 degrees Fahrenheit. So we can assume during those days the buildings or homes are going to be heated. Your vapor entry rate is going to be higher at 4 liters per minute. 62 days of the year in region A, the average temperature is greater than 65 degrees Fahrenheit. So in those days, the buildings, homes not likely to be heated. You have a lower vapor entry rate, defaulting to the 2 liters per minute. So you can do the same thing for regions B, C, D, and E. Look at the climate database and then estimate an annual weighted vapor entry rate for each one of these regions. So that's what we did here, and it's just an example region-specific annual average vapor flux rates that we calculate based on the days, the year that homes are being heated and cooled. So for region A, on average, the weighted annual average vapor flux rate 4.5 liters per minute. Region B, just getting a little warmer, less heating, lower annual average vapor entry rate 4 liters per minute. Region C, to get over to the west coast, California, by now the average number of heating days still 166 days per year, where the average temperature is less than 55 degrees, 199 days per year where it's above that, cooling days and heating days. So the weighted annual vapor flux rate in this case is still dropping to 3.4 liters per minute. Then in tropical areas, southern Florida, Hawaii, the average number of heating days is assumed as 0. The average number of cooling days per year, 365. So in this case, your annual average vapor flux rate is the 2 liters per minute. So now we have annual average vapor flux rates for each one of these 4 climate regions. Next thing we do is look at published information for indoor air exchange rates. So in region 2 or region A, in the cold area, in our paper we assume a default indoor air exchange rate averaged over a year of 0.35 times per hour. This is actually the minimum required indoor air exchange rate for residential homes under a building permit. This comes out to 1,423 liters per minute, and assuming a default house volume of 244 cubic meters. Region B, so now we're getting warmer. People are going to have their windows open more during the summertime or spring and fall times. So you get a higher annual average indoor exchange rate, a little bit over 2,000 liters per minute. Region C, now we're in the Mediterranean area. We're assuming a average default indoor exchange rate of 1 time per hour, so about 4,000 liters per minute. And then in the tropical areas, Hawaii, southern Florida, it's probably much higher than this, but just assuming since we don't have that much data, the same as the Mediterranean areas, 1 time per hour, again about 4,000 liters per minute. So now we have both annual average vapor entry rates into each of the regions and the homes, and we also have an annual average indoor exchange rate, so we can use that to calculate a subslab attenuation factor specific to each region. That's what we do in this figure. Again, this subslab attenuation factor is just the vapor flux rate or the vapor entry rate divided by the air exchange rate in those areas. So you can see for regions A, B, C, D, you see a progressive decrease in the attenuation factor, which means that you see it's an increase in attenuation overall. So in region A, the cold area, the subslab attenuation factor 0.003. So there's that number again that came up in EPA's database, and they actually collected most of their samples in region A. So this approach seems to verify the median of EPA's vapor intrusion database is actually accurate. And again, that tells us something about vapor plume heterogeneity beneath floors, that a lot of the samples they collected were actually representative of vapor entry into those specific buildings. Region B, you see the attenuation factor is decreasing, which means that you're getting more attenuation inside the building. It's 0.002. Region C, by the time you get into the Mediterranean areas, instead of a 300-fold attenuation you see in region A, now we're up to about close to 1,000, actually a little more than 1,000-fold attenuation of vapors intruding buildings in region C, coastal California. And then again in region D, dividing the vapor flux rate by the indoor exchange rate, 2 liters per minute divided by 4,000 liters per minute, much higher subslab attenuation factor, as you would expect, 0.0005. It's not that much higher. It's 6 times more attenuation of vapors intruding a home in Hawaii than you'd expect to see in upstate New York or someplace like that. I'm guessing it's probably much higher than that, so I would still consider this to be very conservative. For one thing, buildings in Hawaii, now they're air conditioning for much of the year. When a building's air conditioned, your vapor flux rate should be 0 because the bottom floor is going to be overpressured due to heavier, colder air. Now we have subslab attenuation factors specific to each one of these climate regions, and we put together a map of what we call vapor intrusion risk regions of the U.S. So the highest vapor intrusion risk region, not surprisingly, because in the areas where it's colder, is the region A. Again, they have higher average vapor entry rates into buildings due to heating, and lower average indoor exchange rates because they keep their windows. People that live in these areas tend to keep their windows closed for much of the year. Whereas you get a much higher rate of attenuation, and again in places like coastal California and vapor intrusion risk region C, Mediterranean climates. So you have a much lower risk there. Region B, if you look at the climate data, coastal Oregon and Washington actually match up the same as the southeast and the southwest. And here you'd have a moderate risk, so more moderate heating of homes during the winter time, and a similar indoor exchange rates due to people leaving their windows open for longer periods of the year. So here's the 4 vapor intrusion risk regions that we included in our paper that we published in 2014, regions A, B, C, D. So I think it's a nice step forward in looking at heterogeneity again, variability in vapor intrusion risk with respect to climate, something we've known for years, but before Soong et al. Published their paper in 2014, and we followed up with it with our paper. I think we hadn't thought about that in enough detail. But now this is relatively simple to do. So in a summary here, that just looking at USEPA's subslab attenuation factors, method 1 versus method 2, we talked about, method 2, the USEPA's vapor intrusion empirical database, very worthwhile to do and compile. I spent a lot of time looking at it, several years, but now we know it's just not technically defensible due to growing evidence of vapor plume heterogeneity. So you can't really make any calls when you collect a small volume subslab vapor sample, say 1 liter, and compare it to indoor air data. You have no idea if it's representative or not. And statistics isn't going to help you with that because it's not going to look at field air in the data. So the comparison of estimated vapor entry rates, again based on very well-founded building leakage models and field studies, to indoor air exchange rates is still the most defensible method for estimation of subslab attenuation factors. And then you can use this to split the U.S. up into vapor intrusion risk regions based on, again, on the building leakage models and such that we just discussed, and regional indoor air exchange rates, trends in those. And the important thing here is now you can calculate an annual average subslab attenuation factor for each one of these regions. So we're not going to treat upstate New York like we are, say, treat Hawaii or coastal California anymore in terms of vapor intrusion risk. We know it's higher in colder areas than in warmer areas. So this is key because now we really need these attenuation factors to develop screening levels so that we can especially screen out low-risk sites very quickly and screen in high-risk vapor intrusion sites very quickly so we know where to focus our resources. And then we can use soil gas data collected, say, from the center of a slab or a slab area closest to the source or say on the downwind area of the slab for worst case screening. The question now is, it wasn't a problem with the collecting soil subslab vapor samples in the past. It's still important data to get, it's just how you collect it. So how can we collect representative subslab vapor samples now that have some tie to the objectives, vapor intrusion risk, instead of just the size of a suma canister that the laboratory happens to send to us for testing. So we need to get away from collecting discrete samples in vapor intrusion and subslab vapors, the same as we've gotten away from collecting discrete samples in indoor air and in soil. So again, we published a paper in 2014 on a discussion of EPA's empirical database and estimation of subslab attenuation factors. A key point here is, even though the paper came out in fall of 2014, it was too late to include it in EPA's vapor intrusion guidance they published in 2015. Most of the reviews of that guidance were completed in 2010 to early 2014, or even earlier than that. So I was discussing with the people who published that guidance document. They said that they couldn't go back and review our paper, just considered additional information post their guidance. Our paper was referenced in the USEPA's 2015 Petroleum Vapor Intrusion Guidance, a much smaller group of people, easier to get things done and discuss with the different stakeholders in it. So here's something coming soon. You can take the same vapor intrusion risk regions and apply it to individual states. Here's how it would look if you applied it to California. Again, we go back to the county-specific climate database for California, and in this database, for every individual county in California, they estimate the number of heating days and the number of cooling days. Once you can do that, then again you can estimate an annual average vapor entry rate into homes for that area, and then we can also look at indoor exchange rates for those areas. It's just something we put together pretty quickly. We're going to give a presentation on it next spring at the AHS conference. But it makes sense. The vapor intrusion risk region A, higher vapor intrusion risk than you would see, say, in the mountains in the cold areas of California, than along the central coast zone in San Francisco, where you have lower rates of vapor entry, less heating, and higher indoor exchange rates. So we can do this now. This is just an example to get us started, and you could vary the resolution of this by breaking it up even more climate-based regions and such. But this is where I think we should be going. So that's how you would evaluate vapor intrusion risk, more climate-based methods. Next step is, well, how do you collect a representative sample of subslab vapors? Again, that's very key to connecting contamination you find inside of a building to subsurface contamination. Huge deal for property owners and people responsible for contamination, since they're legally responsible for this. So the subslab vapor data is very important. So this is something we just started a field study with. We get a lot of grant money from EPA Region 9 to carry out these small field studies and just think about these issues more. So the first step back, you have to go back to sampling theory, just like we did for soil, is what's your decision? What are you looking for? And this is what the indoor air folks have been looking at for years also. What specifically are they trying to characterize? Is it a single discrete sample in indoor air collected instantaneously in a 1 liter canister? Well, not at all. They're trying to estimate mean VOC concentration for air flowing through a building over days or sometimes years. This is all sampling theory. So how would you apply this to subslab vapors? But what we're looking at now is just as an example, is let's take the average vapor entry rate into a building based on EPA's default, in California EPA and US EPA's default vapor entry rates of 5 liters per minute. It works out to about 7,000 liters per day. Let's call that our decision unit. So in this particular building, It's assumed that 7,000 liters of vapors are going to intrude through a hole in the floor, a gap in the floor in a single day. That's actually our decision unit. So the next question is, what's the concentration of PCE or any VOC in those vapors? And we can use that looking at indoor air exchange rates to estimate impacts to indoor air. So we have our decision at 7,000 liters. The next step is how to collect a representative sample of that. So we finally found a place in Hawaii. I've been trying to do this for several years actually, but we just don't have that many vapor intrusion sites in Hawaii, thankfully, to look at. But we want to carry out a field study of how to do this. How do you collect a 7,000 liter sample, more specifically a 7,000 liter decision unit volume of vapors under a slab? This is a former dry cleaner. It just became available a few months ago, or this summer. It's in Honolulu near the airport. So the building has been completely demolished, and it was too nice to pass up to be able to do some type of detailed field study. It's about 100 by 100 square feet. The slab is intact, in very good condition. In case I forget to mention in a minute, there were some gaps in the floor where there were floor drains and such, and we sealed those before we did any of our vapor sample collection. So here's data from 2012. This building was torn down. It's going to be a new light rail station. They collected some passive soil gas data under the building slab. You see the red spot again in each one of these. They found high levels of PCE and TCE under the slab. But again, a big red flag goes up in my opinion. The hot spots here are based on single samples. Anytime you see single sample hot spots, you really don't know if you could be dealing with small scale variability. And these could be artificial patterns, but it tells us something. It tells us that there are high concentrations of PCE, especially under the slab. 99% of the vapors are PCE, just a small amount of TCE, or 90% or so. 2016, earlier this year, went back and they got a sumacanister data, some active soil gas data, and you see the high concentrations they found here, PCE under the slab, up to 108,000 micrograms per cubic meter. Just to put that in context, this is actually our residential. It's wrong on this slide. Subslab vapor screening level for vapor intrusion in Hawaii is 920 micrograms per cubic meter. It's much higher for commercial industrial. So that was an error in this slide. But anyway, the sumacanister data, active sample data here, definitely indicated a significant vapor intrusion problem. Just hypothetical case someone were to put a house on top of this site. Now when you compare this data, I'm not going to show it in detail to the passive sample data, but not a big surprise, your hotspots start bouncing around. So the hotspot based on the SUMA data is a different location than the hotspot based on the passive data. Again, that just tells you that you're dealing with a lot of small-scale variability in the vapor plume under the slab. Not surprising, it was a dry cleaner site. Very little PC in the groundwater. Most of the contamination is within 0 to 8 feet below the bottom of the slab, and it's trapped in soil. It's probably wastewater going through drains and such. So here's how the approach that we're developing now to look at subslab vapor and incorporate this into a vapor intrusion investigation. First thing we're doing at this site, and this is going to be excessive for most sites, we understand, but we split the slab up into 25 grid cells, about roughly 10 feet by 10 feet. And then within each cell, the next step is we're going to identify where the high concentration areas of the vapor plume are, and we're going to collect one sample within those areas. So we're going to just step back, then we're going to initially do that with passive sample data. So we split the slab area up into 25 grid cells. We could put one passive sample within each grid cell, but how do we know that's accurate or representative? So what we're doing is we're putting 4 passive samplers in every single grid cell. These individual samplers for each grid cell then are combined at the laboratory for testing as a single sample. So we're installing, in this case, 100 passive samplers through the floor of this slab, but we're only getting, the lab's only analyze or carry out 25 analysis because we're putting them together in groups of 4 for each particular grid cell. Then we're going to use this data to identify large-scale vapor plume patterns under the slab. In the green areas here, how do we know that these 4 passive samplers are representative of that particular grid cell area? Within the green areas, we're putting in 3 sets of 4 samples each, and we'll test each set separately, and then we can look at the field precision of an individual set of passive samplers. In the yellow cell, we're going to install 9 passive samplers. We only got 6 in, ultimately in the field. But then we're going to test each one of those individually just to look at small scale variability between co-located passive samplers. So a very intensive passive sample investigation to look at heterogeneity and get an idea where the higher concentration areas of this vapor plume are. So we installed these earlier in August, the passive samples. This is just an example of the standard grid cell. 25 of those, the orange spots where we installed a passive sample. And again, we're going to combine all 4 passive samples in for a single analysis. We're doing this through Beacon Environmental, and they've agreed to combine them into one sample for testing. Here's an example of one of the grid cells where we're doing replicate samples. So each color represents an individual set of passive samplers. Again, there are 4 each, so they'll all be combined individually. We'll get 3 sets of passive samplers for each of these 3 grid cells, test each one individually, use this to look at the field precision of the passive sample data for an individual grid cell. And here's the area where we can install the 9 individual samples or passive samplers and test each one. In the end, we only got the 6 samplers on the left installed, so we hit the footing, and the 3 passive samplers on the right along the slab weren't able to install those. And that was an interesting thing in the field. Something else we learned in the field is we're not really concerned about the vapor concentrations under the footing, which here might be 2 or 3 or 4 feet thick. Really, we're focusing, our DU is the vapors between the footings, under the slab and around the slab, the vapor plume between the footings. That's our decision unit. So that's where we wanted to install these samplers in the first place to look at. So here's the hypothetical results of our passive sample test. This is probably way too simplistic, but in this case we show a hot area near the center of the slab. So this, ideally we would identify this, and then next thing is we go into this hot area of the slab and collect a single very large sample. Or it's not really a sample, that's where we collect our decision unit volume of subslab vapors. So this is an example of what we're going to do in this month. We installed the passive samplers in August. Sometime in September we're going to purge 7,000 liters through a hypothetical vapor entry point that we put through the slab. In this case I'm showing it in the hypothetical hotspot. Once we get our passive sample data back, we actually can't wait to get our data back because they're going to rip the slab up, so we're just putting this in the center of the slab. So we're going to install a 2-inch hypothetical vapor entry point in the center of the slab, which is where we would guess the highest concentrations might be if we didn't know anything about the area. And we're going to purge 7,000 liters of vapors through that vapor entry point. And as we purge those vapors, then we're going to collect a continuous sample of the vapors with the 6-liter sumas that are attached to the slipstream, the purge stream. And then we'll get a representative sample of those 7,000 liters we purge through the floor of the building. So we're no longer tied to getting data for a 1-liter sample. We can give you data for any volume decision unit of vapors beneath the slab that you want. Chances are it's not going to be 1 liter. So in this case, the vapor decision unit draw area, we don't know. It's uncertain where these vapors are coming from, and from a vapor intrusion standpoint, it's unimportant. Really, all we're trying to do is mimic the area of influence for this specific vapor entry point, where we decide to draw the vapors from, as if it was a real vapor entry point during vapor intrusion. So the area where the vapors come from doesn't matter. We just want to collect those 7,000 liters that would come up through that vapor point over the next day, 1 day. And we're going to collect replicate suma canister samples as we purge those 7,000 liters just to compare the precision of our field data. We expect that to be pretty close. And we're going to collect a series of these, what we're calling large purge volume decision unit samples to evaluate heterogeneity over time. We're going to collect a series of 3 to 5 7,000 liter purges, or samples from 3 to 5 7,000 liter purges during the field study. Again, we're still working on this, so this is a still draft in the works. So how do you do this? How can you collect what in essence is a 7,000 liter subslab vapor sample? Well, Todd McAllery figured this out several years ago. They've done this at hundreds of sites. So again, just show a little more detail here. You'd put a 1 to 2 inch hole in the slab of a building in some targeted area. If you happen to know where higher concentrations area the plume are, you can collect the sample there. So a worst case scenario for vapor intrusion. Or another alternative is just to collect the sample in the middle of the slab. So the way he does this and the way we're doing this in the field is to, again, drill a 2-inch hole in the floor, and then it's essentially a pilot SVE test, but you hook it up to a shop vac. It has usually about a 6 horsepower motor, and then purge 7,000 liters using the shop vac. This sounded pretty bizarre, I have to admit, when I first heard about it, but in the end it's a great way to do this. The shop vacs they're cheap. You can rent them at Lowe's or anywhere, and you can put in a vapor flow monitor in your stream, the purge stream, between the sample port and the shop vac to monitor the vapor flow. Also within the pipe connecting the sample port to the shop vac, you hook up a series of suma canisters, either one or a series if you want to look at data reproducibility. So as you turn the shop vac on, you monitor the purge rate, and you set your suma canisters to collect a sample over the estimated time that it's going to take to purge 7,000 liters of vapors through that hypothetical vapor entry point. And you do this by doing a pilot test ahead of time and looking at the vacuum that's poured on the hole and such, and run some example purge test, just so you know when you hit that 7,000 liter target volume, the time it's going to take. So this is pretty simple. There were some concerns that you're going to get too high of a vacuum using the shop vac. You're going to exceed their 7 inches of mercury limit for soil vapor sampling. Well, the shop vacs, the smaller ones here, 6 horsepower, so don't have that high of a vacuum on it in the first place, so that's not going to be a problem. There's concerns about leakage, which is that's valid. So we seal the areas of the slab where we expected potential high leakage, some floor drains and such. There's some cracks in the slab. We don't expect to see high leakage there. Where we did, the cracks did look significant, and then we filled those, or some other holes that happened to be drilled through it. And one common problem we've seen, and mistake we made in the past, was looking at expansion gaps in the floor and thinking those went all the way through the slab. In reality, the regularly spaced expansion joints in slabs don't penetrate the entire slab, so they're not going to be a source of leakage unless for some reason they happen to be cracked all the way through the bottom. But as long as the sample that we collect, or the purge that we take out of the vapors, is 90% subslab vapors, and we're quite happy with the data we get from the suma canisters. So again, you purge 7,000 liters, continuous draw with the suma canister, and then you send the suma canister to the lab, and we can assume the lab data represents that 7,000 liter purge, and that 7,000 liters is our decision unit. So here's just an example. We were testing the shop vac just to verify the vapor flow rate. In this case, we got some weather balloons, and we hooked them up to the shop vac and just blew out the balloon with the shop vac, and then we looked at the time it took to blow up the balloon, inflate it to a target 7,000 liters, which in this case for a sphere about 2.4 meters. It took about 7 or 8 minutes. It would take about 3 minutes if there was no restraint on the shop vac. If you put some restraint on the shop vac, increase the vacuum on the shop vac to say 30 inches of water, then it would take about 8 minutes to fill up this balloon to 7,000 liters. So that gave us an idea in the field of how long it was going to take to purge 7,000 liters. And then we actually did a pilot test in the field. It worked out quite well. And we contacted the lab and used that to set our suma canisters, their draw period, which in this case we're setting them for about 10 or 15 minutes. So that's it. That's the field study we're going to do. So we talked a lot about vapor heterogeneity, how to come up with better approaches to estimate subslab attenuation factors, which I think we can now based on climate, and then how to collect more representative subslab vapor samples, which are key in any vapor intrusion investigation. And we're just starting to work on this, but we're working with a lot of people in the mainland U.S., and I think we'll have a nice report out sometime in December. So thanks again for your attention, and we'll keep you updated.